Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at putting math in motion. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to be joined tonight by our two panelists, Tom Stanke and Daniel Wilkie. Tom is in his 28th year of teaching and facilitating the learning of mathematics. He's currently math department chair head at Mother Teresa High School, where students use the TI-Nspire CAS app for the iPad. Tom was pivotal in getting CAS embedded in his math curriculum and has led the way in supporting teachers in their learning to more effectively use CAS and other tools to support improved student learning. Outside of school, you might find Tom tearing around the slopes or riding his bike around the Gatineau Hills. Tom, thanks so much for being with us tonight.
Thank you.
And Daniel has taught every level of high school math, including IB and AP, over the past 23 years in a few different states, Texas, New York, Virginia, and now South Carolina. He's currently the IB/AP coordinator and the IB math teacher at Woodmont High School. Daniel has been married to his loving wife Amanda for 14 years, and they have three awesome children, Cameron, Alex, and Kevin. Other than loving his family, Daniel enjoys educating teachers on all things TI and acting in local theater productions. Daniel, so good to have you with us tonight.
Thank you.
We're expecting a large crowd, so your audio is automatically muted. Feel free at any time to send questions to Daniel or Tom using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Also, at the conclusion of the webinar, we'll provide a link for all the documents that are going to be shared tonight by Daniel and Tom. And there's a lot of them, more documents than we normally have in a typical Tuesday webinar, so that's exciting. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu and choose Audio Broadcast to reconnect your audio. At this point, Daniel is going to discuss our agenda.
Hello, everybody. We're going to be talking about three different topics with our wonderful Math in Motion. Tom is going to discuss the use of sliders in his creative creature activity that he's done with his students. And I'm going to do a couple different activities, one with the CBR2, how we graph some parabolas, doing a little what's called roller coaster rollback. And then we're going to do a little bit of introduction into some basic programming with the TI Rover. I had a little activity that I did with my kids, you know, going from home to school. So those are just a few of the things that we're going to be doing tonight.
Awesome. Thanks, Daniel. And Tom is going to discuss our expected outcomes.
So by the end of the session, a few of the things that we'd like to make sure that you're walking away with is having an appreciation for how you could analyze animated characters, creatively created animated characters using functions and sliders, explore functions and coding to navigate the rover from home to school, an obstacle course with the TI-Innovator Rover, and finally using the CBR2 motion sensor to avoid obstacles.
Thanks so much, Tom. Daniel, you have control. Feel free to share your screen.
Thank you. Wow. All right. I hope everybody is doing well for a Tuesday evening. But basically, the first activity that we're going to talk about basically is this. I was trying to think of what can I do that is a little bit different than the normal activities that are done with the CBR2. And because I love doing the match a graph with the CBR2. My kids really get a kick out of it. When I'm instructing teachers, they really enjoy the connections that can be made. And then I also love the fact that, you know, when I bring different types of spheres or balls in the classroom, we can kind of get nice parabolas going. But I want to do something a little bit different. And so basically, I love roller coasters. And so I was doing some searching online, and there is a roller coaster basically out in New Jersey that I found, and I thought it was a great thing to tackle. But just to give you a little bit of background, roller coasters basically were just, you know, formed from ice chutes. So back in the 1700s, back in Russia, they used to make, well, what we call roller coasters, but they would just use these wooden sleds or ice sleds and go down these ice chutes that were steep, you know, hills of ice, and then just some bumps at the end. And that was what started the whole roller coaster craze. So, and then here's a little quick picture of them. All right, just some of the modern look of them. But this is what I want to talk about. This is what's exciting. This is called King da Ka, and this is a crazy roller coaster at Six Flags in New Jersey. And for one thing, it's just crazy tall. But the biggest thing is there's a little sign before you get onto this ride that says, sometimes you will not reach the top and you will come shooting backwards to start all over again. Because basically you have not reached enough speed to get to the top, to get over the hill, to get over the crest of the hill. And that's called a rollback. So, you know, I had someone who had actually done an experiment with this. And what I would like to do is show you what we did in class to kind of demonstrate this kind of rollback. And it was just something very simple that my kids did. And so I'll show you a quick little video of that, just to kind of, and here's that sign. It says, attention riders, on occasion, the train will not go up the hill. So this is normal, but basically you'll roll back safely and start again, hopefully to get fast enough, you know, to get over. So I just thought, okay, this is exciting. So what we're going to do is, with my class, I had them get a ramp, and we took little race cars. The morning of, I just raided my 3-year-old's toy box and brought him into school, and that's what my kids used. So we had a ramp, and then I have our CBR2s that we use, and I asked them, if we were to place the CBR2 somewhere, where would you want to place it? Would you want to place it at the top of the ramp, at the bottom of the ramp? And I let my kids choose how they wanted to do it. And one thing that I love is, as soon as they plugged that right into the calculator, it was ready to go, and they just started collecting data. So what they did, most of them did choose to put it at the bottom of the ramp. And maybe I'll just show you the quick video. And I have to warn you that the video might be a little choppy, but that is okay. All right, so right there at the beginning was a very nice. That was a better one, much better one. Let's see your graph. So that was basically what I had my students doing in class, just to generate parabolas. And some of the parabolas, oh, one thing I really need to show you first. Sorry to interrupt, but if I would have just waited 2 more weeks to do this activity, I could have worked with my physics teacher, because they were doing their block car racing in their own physics class, and I could have used those exact cars. So I just wanted to show you a picture that if you are good communicators with your science teachers, or if you're a science teacher listening in right now, please communicate with your math teachers, because you could be sharing stuff and doing stuff together. So I wish I would have waited 2 more weeks to do this, because I would have loved to have used their stuff and kind of went into their class and did it. So always communicate. I need to do more of that, but always try to communicate with one another. So what I wanted to show you is a couple pictures. So some of the graphs that my students had generated just from pushing the card up and collecting the data, getting the parabola. So I had 3 different samples that I provided here. And what we had the students do then is basically try to find the parabolic equation of their curves. And once they found those curves, those equations of the curves, it was up to them to then plug it back into the calculator to see how closely they fit it. Again, I don't know if you are an Nspire user or if you're an 84 user. I myself prefer the Nspire. The CBR2 can plug and play, but I definitely prefer the Nspire with this. And so it was just nice to be able to collect that data immediately, have the students work on the equations for a good chunk of the class, and then take their equations and plug them back into the calculator to see how closely they fit. And some of the results I got here. So you'll see that with this data, they got pretty close to their data, which I was pretty happy with. So like I said, they did their best. Yes, and thank you. For people who are the 84 users, this does, like I said, plug and play with it very nicely. So if you only have 84s at your school, and the CBR2s or the CBRs, definitely. Those are something we need to use because you can generate this wonderful data. And I allowed my students to select the type of equation that they created. Some of them used vertex form, some of them used the zeros form, some of them used just the standard form. But it was really up to them how they wanted to do it. But I had a lot of good responses with their work, so I was very happy with what we went. So, and again, this was just pushing a cart up a ramp, just because their teacher loved roller coasters and saw this cool thing about rollback, right, online. So, kind of going back to that, once we, collected the data and then we found the equations, all right, then we got to discuss, right? Because when I teach, if I'm doing most of the talking, and I say that as I'm doing most of the talking right now for the last 10 minutes, but I love to hear the students talk about their results and what they can do differently to make it better. So that's what I would like to ask you right now is if your students graphed this equation, and let's say it wasn't the perfect fit, what type of discussions could that lead to? All right. So anybody have anything to share? Where could you take it if their parabolas their equations did not fit their data? All right. What kind of discussions could you have with them? Okay. So one of our wonderful attendees said friction. Okay. Okay, again, why isn't it a perfect fit? What do you need to change? And then in the back of my mind, I can get into a nice discussion with transformations. How can we use transformations to make it fit a little bit better? And why didn't our work in the first place, if we're using points that we collected, the data points, why aren't we exactly getting a nice fit for that curve? What is wrong with our math? So there's a lot of discussion that can go into place there. And I'm loving Oh, I love the things that are popping up. So, and then and the last question that came out is, how do we tell if it's a better fit? One is a better fit than the other. All right. Just generating discussion from these simple activities. So we get to use the CBR2. We get to, collect data. We get to analyze data. And then your students get to discuss it. So basically, that's what I love in a math classroom. And as I'm kind of growing, I'm learning that's what science teachers love too. So, and that's another, oh, thank you, Jeannie. Another great question is, you can compare. If you notice, I had 4 different vehicles showing in my video. Well, why would one vehicle give me a different curve compared to the other? All right. So we can start talking about that. All right, that is awesome. And that's another reason why I wanted to use my physics teacher's vehicles, because they were all a little different. They were all weighted a little bit differently. And that would have been a great discussion to have too. I am very big in discussion amongst my students. So that was really my first activity. Curve shape, could you? Sure. So I just want to take it one step back to relate it to the actual roller coaster. We talked about the parabolas. So one important piece is, what does the parabola actually mean to the roller coaster? Because we're comparing kind of a position in time. Okay, so the position traveled away from CBR2 in a certain length of time. So if we're simulating going up the hill on the roller coaster and then unfortunately having a rollback to come backwards, what is our parabola telling us? So are there any specific pieces to that, all right, to that parabola that specifically relate to that roller coaster? All right. Anybody want to have any closing sharing remarks before we move on? Because I'm loving the comments that are popping up. Yes, coefficient due to gravity. Oh my gosh, thank you for throwing that out there. All right, so there's so much to talk about here. So I love. So anybody have anything else to share? Awesome. Yes, when the students collect the data, they are doing it. They are taking ownership. Oh, initial velocity. Ah, yes, thank you. This is great stuff. I love seeing those comments. That makes me so happy. Anything else you want to share? So, I recommend going to New Jersey to try this roller coaster. It is truly scary but amazing. So, Tom, I think I'm ready to hand over to you to the second part. Are you okay with that?
Perfect. Yep.
Cool.
There we go. Okay. So my little segment here is motion, but in a different way. Kind of, I'd prefer to call it moving math, both in an emotional sense and in a physical sense. So I was searching for something that would have my students transforming and constraining functions in a purposeful way. One idea I had was fitting functions to data, and we'll look at that in a moment. The idea of creating a character mathematically seemed like a really interesting opportunity to allow for some creativity on the part of my students, though. So through the activity I'm going to share with you, I wanted my students to think about the connections between the things that they had already learned in relation to functions. So, Mike, if you could maybe push out that poll. I personally attended a music school for 11 years. Then I studied engineering at university. And now I've been a math teacher for almost 30 years. And I remember going to my faculty of education, and I was shocked to see how many of my fellow math educators came from an artistic and creative background. So I'm curious to know kind of what proportion of you folks kind of on joining us this evening that are math educators have some kind of an artistic or creative background as well. And the results of that poll will pop up in a moment. Yep.
Sorry, Tom, if I could just jump in real quick. So I did just start a quick poll. It's only one question. Would you describe yourself as artistic and creative? And those of you that are joining us tonight on a mobile device won't have access to this poll, unfortunately, but if you're on a computer, feel free to look at the right side of your screen, probably the bottom right, and there should be that one question that you can click yes or no and then submit, and I'll give you about 15 more seconds to do that. Thanks, Tom.
Okay, and I'll keep kind of going with mine. So this is a favorite little cartoon of mine that I've had kind of in my back pocket for many years now. But I always felt there must be a better way than paper and pencil testing, right? The little joke there against animal testing. Like if students learn in a certain technology-rich environment, collaboratively, and with far less time constraints, then I wanted to somehow bring those elements to the way I was assessing them. So that first idea that I shared with you, one of the files that Mike will share with you at the end of this is the baby boom data. So I had students fitting quadratic models to Canadian baby boom data. I'm assuming that American data would be quite similar. It shows the number of births per year, which is meaningful and purposeful use of transforming and constraining functions. You notice that I kind of chopped off my quadratic model starting at around 1947, I think it was. So it's a math teacher with an art degree. But I thought this is neat, and I actually am very interested in data, but I didn't find it really tapped into my kids' creativity doing this. So I played this kind of what-if game. So this seemed like there had to be a better way kind of digging into their understanding of function transformations and at the same time tapping into their artistry and creativity. So this is the idea I came up with. And it was a bit of an experiment last semester for me. And kids always want to know, so what are you looking for, sir? And I wasn't quite sure. It was the first time I was going through it, but I thought, okay, could you guys use all the different function models that we'd played around with up until that point well? So linear models, quadratic models. They dug a little bit into conics, but not too much. Ideas around analytic geometry. And so then I threw in some kind of artistic, non-mathematical ideas that your creature is recognizable. I realized, and they were using TI-Nspire CAS on an iPad, that you could kind of cheat by using line segments. So I wanted them to minimize doing that, although vertical lines became a bit of an issue. Color, you can use color. So I wanted them to be creative with that. And finally, the motion idea, that they could creatively use sliders for motion. And I'll kind of show an example of that in a moment. Do we have the results of the survey, Mike?
We do. We got results of 34% said yes, they would describe themselves as artistic and creative. Yeah. 27% said no, and we had 39% that were not able to answer.
Yeah, so I guess the degree to which you see yourselves as being kind of artistic or creative might be the reason. But it's significant, and I've seen it throughout my mathematical career. It's an interesting association for sure. So day one, I'll walk you through what I actually did with my students. This is a picture of my classroom, and you'll notice the kids are up at the whiteboards in groups of 3. They're actually visibly random groups of 3. So every day I greet them at the door with a deck of cards, and they get a card, and that's their group number for that day. And they sit in groups of 3, and they work at the whiteboards. And there's blackboards at the front too, but in general, kind of there's whiteboards around there. And the whiteboards I refer to as vertical non-permanent surfaces and visibly random groups. So that's just kind of our normal way of being every day. So then I kind of set the kids about conceptualizing and designing their creative creatures. And I'm going to share a quote here from a report from one group. So they write, "On day one, our first day was spent brainstorming creative monsters to create on our TI-Nspire app, taking into account which functions we would use for certain parts of our creation. Our final decision was to make a butterfly. As seen on the left, I'll show it to you guys in a moment. We had many ideas for possible functions that we would include. Our finished product is a much neater idea than our concept art." So I made them take a picture of the work that they were doing on the first day. So just throwing ideas down. There were no bad ideas. And then beginning to think about the mathematizing of those ideas. So day two, I wanted them to construct their creature by transforming and constraining functions and introducing ideas related to color, motion, and we'll see a group in a video in a moment doing this. But I'll read the quote from a report from that same group on day two. "The first part of our second day was used for experimenting with different functions we could use for our animal. After learning that hyperbolas, which were to be used for our butterfly's wings, were impossible to restrict." Just a personal note for me here, like they were searching for things that would fit that just weren't linear or quadratic. So they were investigating and finding all kinds of functions that we hadn't even come across. We hadn't really done anything with trigonometric functions, and it started showing up too. It says, "We struggled with finding an alternative function for them. At this point, we only had the head, antennas, and the body. That was the day that we worked on making the parts of the antenna move in unison. We also decided to experiment with equations such as y equals sine x and y equals root x, both of which we ended up using. We did not, however, use y equals the absolute value of x." Now, none of those functions we'd actually learned about, but they were kind of searching for things that had certain characteristics, although this was considered for the antennas. So here's a little video of, this is a grade 10 group right now. So I guess in the American context, it's similar to your Algebra 1, Algebra 2. So let me play. You probably won't hear the sound, so I'll kind of talk over top. But this is one group, and you can see them hovering over their iPad. And it's interesting, you can actually embed actual pictures for the less artistic among the crowd, and then they could kind of trace around it, trying to fit their functions. This was on their day two when they were taking their concepts and trying to render them mathematically on their iPad. Okay, oops, sorry. There we go. All right. So this is from the one group that was working on the butterfly, and it's just like the thinking that went into it was just unbelievable. They really poured themselves into it, and you can see kind of the color coordination between all the different function parts that they had for this butterfly. And I don't know if you see the sliders up top there, but that was a real chore for them, getting their function to move, but kind of stay constrained where they wanted to. For instance, how do I make sure that the parabola antenna kind of stays parked at the head, at the top of the butterfly's head, or the eyes were doing funky things, and they tried having the trigonometric function pattern kind of do something too, but they really struggled with that, and it was really fascinating to watch. I'll maybe show you just for a moment what this looked like kind of when we're actually watching the animation of this. So I mean, they didn't go crazy with their color. Their thinking kind of was more around the parts of this. I just wanted to show you how simple some of this stuff is. So those of you that haven't used, this is the context of the TI-Nspire, but if I do a times x squared, for instance, it'll automatically ask you, oh, do you want a slider for a? Okay. And then away I go. So it really takes very little upfront understanding, right? And then animation is one of the things that you can play around with that. I'm sure those of you that have used this for transformations, it's pretty straightforward. So, but I don't want this to become a kind of button pushing exercise. Oops, there it comes. Let me go back to here. There we go. All right. So we're on to day 3. That's their groups. So here you're looking at Carter, Leigh, and Hannah. I'll show you a couple of other ones here. So this is from Laura, Bridget, and Zia. Fiona, Ryan, Natalie. Sarah, Avery, and Nelson. Caitlin and Jada. Oh, one thing I wanted to share with you too, just before, just like how they immerse themselves in it. This is the report of the group that did the butterfly, and I'll just kind of cycle through this. So it's kind of almost like a kind of mini diary of their day 1, their day 2. Here's their function models they used. But I tried to get them to document their thinking, right? And just take a look at what they came up with. And this is a document that will be shared with you at the end. It really is amazing. And what I loved was kind of the risks that they were willing to take and how they stepped outside of the boundaries of, you know, in this course, we're only supposed to learn this functions. Who cares about this course? Like, they were wanting to achieve something, and that was the thing that was driving what they wanted to do. So there we go. I'm not sure if I wasn't really monitoring the chat very much, so I don't know if Mike or if you saw any questions that were posed that maybe I could respond to.
Yeah, Tom. What unit do you associate this with?
Well, I mean, if you're playing around with transformations of functions, if you're getting into function notation, and again, our Ontario curriculum is different than the American, a lot of the Algebra 1, Algebra 2. We have a much more integrated curriculum, so we'll integrate kind of geometry ideas with function ideas and algebraic ideas. So for myself, this is after they've learned some of the transformational ideas in the quadratics unit, which they would have learned in the 10th grade. They're taking with them some of the stuff from linear models from grade 9. We've done some stuff with analytic geometry as well. So that's kind of the mathematical background they bring to it. But what really, yeah, so Algebra 2 pre-calc, it sounds like, is a good fit for you guys, eh?
Yeah.
Sorry, what was that about the iPad students? I missed that last one. Yes, it is Algebra 2, yeah. So it's one of those things, like they didn't learn anything about trig functions or exponential functions or absolute value functions or radical functions or rational functions, but they were actually playing with those functions, which was kind of nice, right? So the whole idea of transformations of functions had a purpose, right? And I loved how some of the kids that didn't normally shine really shone, because it did tap into some of their creativity, and you could really see their excitement and their investment in what they were doing. So,
how much time do you give them from the start to the end of this activity?
I dedicated 3 days. So one day where they were just conceptualizing at the whiteboards. One day where they were kind of mathematizing things in the iPad, but they were kind of coming up against lots of obstacles and really struggling, and you'll see that in the report that I shared from the one group. And day 3 kind of was where they really documented all their thinking and cleaned up things. So they obviously took a lot of these things home with them and did their own research, and they were really persistent in trying to solve the problems that they were encountering during the day.
Tom,
Okay.
I just want to add, because as you're showing this, I was thinking about my own students in my own classroom, my own Algebra 2 students working with families of functions, things like that. And I had never really considered allowing them to just play with all the possible functions that were built into the calculator, things that they might not see in Algebra 2, but they might see in calculus or pre-calculus or some upper-level math courses. And I just think that's pretty slick. The Nspire in particular, for those of you that aren't familiar with it, has lots of built-in templates. So students that may want to use a circle, it already has a template for the circle, general form of the circle equation, things like that. So it allows students to just substitute numbers in and press enter and see the graph that's generated and say, oh, that's not what I wanted. I want it to be wider or taller or shorter. And they can start just messing with the numbers and starting to learn, like Tom said, about transformations, things like that. So I just wanted to add that.
Perfect. I think I'll bump it back over now. Is that okay? Or are there more questions? Reminds me of programming. Yeah, in a sense, it's true. So I'm just going to stop sharing my screen right now, and I'll bump it back over to Daniel. There we go.
All right. Why do I keep on that? All right. Welcome back, everybody. So basically, the last little bit here, we're going to talk about the TI-Innovator and using it to do some simple basic programming. So just give me a little sense. There's about 100 of us here communicating with one another. Has anybody ever used the Rover or done a little programming before in their math? Ooh, I got some yes. I own one. That's awesome. Because if you're not familiar with the Rover, no Rover but program not good. No, yes, cool, awesome. Oh, got some Lego. All right, the NXT. No Lego. No, saw the conference in Texas. Good job. Oh, I love this. Student purchase, awesome. Basically, I teach, IB math, but I also teach what I like to call Friday programming. I do coding Fridays in my class. And what I like to do is every Friday I do a little bit of coding with either the Nspire, and just then I've gradually introduced the Innovator to the students, which is the TI-Innovator Hub, which is kind of the brain inside of the Rover. And then finally, my principal was very kind and purchased a handful of these Rovers for me. Since some departments didn't use their money for some reason, I don't know why, he said, you could use it, go ahead. So I got to get some Rovers, and so now we play a little bit with the Rovers. And what I wanted to do is just, since they are really first-time coders, first-time programmers, I didn't want to do anything too terribly difficult, but I still wanted them to get out of their seats, get moving, and start incorporating their everyday life into what they were doing with the Rovers. So, and that's how I just came up with this very simple activity, which I asked the students to program a Rover to go from their home to school. And for those people who are wondering, because I just saw a question pop up about the cost of a Rover, it depends on the vendor that you use, but they're basically, for the Rover itself, it is about $115, $120. But then you also need the Innovator with it, which is about $55 to $60. So if you combine those two things, I saw somebody pop up about $170, $180 for the Rover and the Innovator Hub to work with it. But then you also need As another person just said, donors choose, I got two. So yes, there's definite ideas out there to help you get that money. But you do need a calculator, as you'll notice. And Mike Houston says, yes, please visit TI-Education.com to look that up. But you'll notice that the calculator fits on top of the rover. And so what my students do is basically they program in to the calculator what they want it to do, and then that speaks to the Innovator Hub, and then, of course, that keeps going. It makes the rover go. So we have just the TI-Nspire CX in my class. I could also use the TI-84 CE. Thank you, Stacy. That popped up just as I was mentioning it. So if your school is a 84 CE or an Nspire CX, then either of those can work with the rover. And since I have the Nspire, basically that's what I'm having my kids program on. Does not work with both CAS. You can have either the CAS or just the non-CAS. All right, so either one of those will work for it. I have one teacher with CAS that borrows them from me, and then I have the non-CAS, so they both are user-friendly. So what I had my kids do is just use simple commands. All right, I asked them to go onto either a Google map or their iPhone maps or whatever, and basically just plot a course. So here is a simple course from somebody's home to our school. And so what I wanted them to do is, basically have the rover program to follow that. Now, you'll notice that there are some slight curves in there, but there are basically a few left turns, a right turn. And I kind of left it up to the students about how accurate for the first run they were going to be. So what I had them do is, if you can just do straight lines, that is fine, okay? We can extend a little bit as we progress from week to week, and you can kind of add the curves in there where you think they would be. But I just want simple, basic programming to start. So all I wanted them to do was first, make it go straight, make it go forward, make it turn left, make it turn right. So very basic commands. Some students got a little fancy and decided to, when they pulled into the school, they wanted to turn around and back into their parking space, which I thought was a little nice little touch there. But it was very simple programming. So here's just a quick little sample of what the programming was just by using simple forward, left, right, backwards commands. For those people who have never programmed before on the Nspire, it's a form of TI Basic that is very menu driven, very user friendly. My kids, I started with some statistics kids who were really uninterested in math. They were really just taking my class for a 4th year of mathematics so they can graduate. But when I introduced doing coding on Fridays, yes, and the TI-84 CE uses TI Basic as well. So I just introduced just basic coding to them, and as the Fridays came closer and closer, they kept asking me, are we going to code today? Are we going to code today? So they were getting interested into it. So they picked it up, honestly, within 2 Fridays of how to do it. Now, they haven't mastered everything that's available on calculators, but I really wasn't asking them to do it. I just wanted them to explore, have a little fun with it, and maybe pique their interest for something they might want to do later on in life. So as you can kind of see from my screen here, after we've connected, the calculator and Innovator to the rover, okay, and I noticed that people are talking about different forms of language and different types of robotics. I'm not fully aware of what languages can communicate with one another. So that is something you're going to have to ask TI. So basically, basically, with this program, I mean, all I had to do was move forward, and then you'll notice that there's a 4 after it. There are some basic units, some default units that are used. Michael Houston, give us a call at 1-800-TI-CARES. Awesome. So the default unit is centimeters. It's every one unit is 10 centimeters. So basically, when I say forward 4, it's going to go 40 centimeters. And then when you turn left or right, it basically needs an angle measure with it. So when I have that 90 after left, it's going to turn left 90 degrees. So degrees is the default. And that's all I really wanted them to do. And yes, you can change the units if you want. But I was just asking them to be very basic and just do basic commands. Their job was, once they had their map, they had to convert the units that were on the map to something that could be equivalent to driving in our classroom. So they sat down for, you know, some time and kind of worked out those measurement conversions in my class. And then they just started the program and started to play around with it. And this is what we did for maybe 1.5 Fridays. We basically just kind of did the basic program. You'll see it wasn't too very long, this first one that I had them do. Very simple, just going forward, left, right, you know, they did a little backwards. And then what we did is we progressed. But let me show you a quick little video. Hopefully it won't be too terribly choppy. So this was them. This was just the basic command of following that first map I showed you. They started at home and then followed along. I know it's a very, very exciting video. So they didn't use any commands other than forward, left, right, and then eventually they did a little backup. So they just used some very simple flags there to tell when they were at school. And then, unfortunately, they did run over the flag at the end. But that was theirs. It's a very simple thing that they did. So then, as we progressed, I asked them to throw in some obstacles. All right, so what would you change about your program so that you would actually try to avoid an obstacle? And this is when we had to start to get a little more advanced, because what we were asking them to do is use the Ranger sensor that is on the front of the rover. So if I go back to my picture, for those people who are unaware of the rover, so this right in front, all right, is basically what we were just using with the CBR2 with motion sensor, right? It senses distance. So what the kids had to then do is turn on that sensor and then program it to basically say, if we reach an object, if it's a certain distance away, then we need to either turn right and get away from it, or turn left to get away from it, and then continue on our path. So that was just a little extension. And what you'll notice about the actual program that's written here, there's a little more advanced programming for people that basically is just more than just left and right. So you look at our for loops and while loops in here, that basically when it's in the for loop, basically it's running a certain distance. So you'll notice it's from 1 to 10 and driving forward 20. So it's really running 200 centimeters there. So basically it's going to keep going and going through this for loop, and it won't stop until it gets to the end of that length. And then within that for loop, we have a while loop That's basically turning on the Ranger to sense if there's an object in front of it. And I hope I'm not confusing anybody with that, because me, myself, I've been coding for maybe over a year and a half now, so I'm still a baby when it comes to using coding. And honestly, the best thing that I have used, and this is a TI webinar, and I'm going to promote TI as much as I can because I use the TI website. For those people who have not been on the TI website in a while, basically you need to go see TIeducation.com, check out the 10 minutes of code, because if you go under TI Innovator Hub 10 minutes of code, the last 2 chapters of that, the last 2 units, are dedicated to the rover, and you can kind of learn to use the basic commands and then get into even a little bit more with a little bit more with the for loops and the while loops. And actually, I used one of those as a guide for this. And then I'll show a quick little video with this involved in it. So what I had the students do is put down some, I just used these little blocks as obstacles. And so when we were starting the program, it would sense these blocks and turn left. All right. And so the kids then had to expand on this code, and what if we wanted it to turn right? What if we wanted it to go around the object? So that's what they had to work on with this program. So it started off as a very simple 1.5 day activity where we just took maps, altered the scale to what our rover to do in our classroom, and then we expanded. Once that 1.5 weeks was over, after they programmed it and made it kind of their own, then we went a little bit further, all right, and then used this even more, which I love. But one thing I do have to to warn you about the rover, just a few things, and I learned this quite recently, that the actual rover is calibrated to run at optimal levels on a piece of paper, because I saw some of your comments talking about the little pen holder that's in there. So there's a little pen holder. You put just an Expo dry erase marker in there, and basically it'll trace the pattern. Some people were talking about polygons in the chat window, and there are programs out there. You can make your own programs to create polygons. So the idea behind the rover is that if we wanted to draw on something, then we want to draw it on paper. And so the wheels are calibrated, the whole system is calibrated best to be on paper. So as you can see from my picture here, it's on a nice slick tile floor, and it runs all right on that, but the wheels, and especially the ball in the back, sometimes slip on there. So it is very easy to get slightly off course with respect to that. So just keep that in mind if you're going to use the rover. And also, please make sure that the floors are clean. I picked up my rover when I was done, and it's a little disgusting, but I found hair kind of curled up in the wheels. So just make sure that your floors are nice and clean before you start using your rover. But then we start talking about, well, how can we compensate for our terrain? All right. And then the kids will have to adjust their coding to basically deal with that. Friction, I love that. Friction. So that was just a simple activity. And like Mike said at the beginning of this, we have all of the documents, the PowerPoints and the documents uploaded for you to use and, you know, go with and do what you want with them. But really, it's about exploring. This is so new to TI and to all of us. I mean, this just came out in the fall, and a lot of us are still getting used to what it can do and how we can push it to its limits. I mean, there's so much stuff now that they're working on that you can plug extra sensors in there, because right now there are 3 sensors. There's the Ranger in front, There's a color sensor underneath, and then there's a brightness sensor on the back. So a lot's going on there that are included with the rover. But then you can also plug in other sensors, all right, into your Innovator that are attached to the rover. So lots of sensors that we're going to be using in the future for this. And that's why we need teachers' help, is to practice and play and share what they're doing with this. This is just a very basic, simple program. So I'm hoping that out of the 100 people who are here with us today, and if they have rovers, do something cool, share it with all of us, because that's kind of what we're doing here. What can you do with a rover? And also on the sides of the rover, for those people who haven't seen it, there are also Lego attachment holders, so you can place Legos in there and make attachments come out there. A few weeks ago at the TI conference, I saw a model where somebody had attached 2 more Ranger sensors to the Lego pieces, so not only was it a Ranger facing forward, but it was also Ranger facing downward. So if you were at the edge of a table or something, it would also make it stop because it senses the end of the table. So it's just stuff like that that more and more teachers are coming up with cool ideas, and that's what we're hoping. But I'm running out on time here, and I'm going to turn it over to Mike, unless there's questions there, and I'll be happy to answer some.
Thanks so much, Daniel and Tom.
Yep.
So I do want to bring you to our website, education.ti.com. Because Daniel was just talking about using coding with his students, and that he didn't go to school for coding. It's not in his background, and it's something that he kind of taught himself. One great place to do that is on our website, and if you move under the Activities tab, near the top middle, there's a TI Codes choice. And so you'll notice that you can do the coding on the 84 plus CE or the TI-Nspire as well. And there's also 10 minutes of code for the TI-Innovator Hub. So if you pick the technology that you're using, and let's say you're just trying to start to learn how to code on the 84 plus, there are built-in skill builder programs that allow you to work at your own pace. It gives you screenshots, things to try. I went through these on my own, and they're really written really well. I also am not a coder by nature. Coding is not in my my repertoire, but I'm learning a lot. So please feel free to visit our website and check out the 10 minutes of code. To receive a certificate of attendance, go ahead and click that link in the chat window. Also listed is a link for the documents that were used tonight, and again, there's a bunch of them by Tom and Daniel. They really hooked you guys up with a lot of documents that they used tonight. So please feel free to visit those 2 links. If for some reason they're not working for you, just hang tight. You'll automatically get a follow-up email in a couple days. In that follow-up email will be a link to the recording, so you can go back and rewind and follow this at your own pace, as well as a link to the certificate and a link to the documents. If you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. If you have any further questions, or maybe we might have missed a question tonight, feel free to give us a call at 1-800-TI-CARES or send us an email, ti-cares@ti.com. We'd love to hear from you. Thanks so much, Daniel and Tom, for everything you guys shared tonight. It was really exciting.
Cool. Thank you.
Thank you. That was fun.
And we hope to see everyone back online next week. Have a great night.